Today's topic is about once we have electricity, a form of energy, electrical energy, what do we do with it? Right? Because it's not just enough that, yay, we have electricity, but like we have to do something with it. I would suggest that one of the first known, is everybody listening, by the way? Thank you. One of the first known stories involving electricity would be Ben Franklin and his kite. Anybody ever heard this story where he supposedly was out in a field and he had his kite out and the lightning struck the kite and he had this revelation that this was electricity? Well, that happened like 200-300 years ago. He wasn't able to do anything with it yet, though, right? Even though maybe he recognized, hey, these are electrons moving, it's not enough until you actually make a device that utilizes it. And one of the coolest things about our current society is that, like I have on the slide here, we use electricity to do so much stuff. Now, the device that uses the electricity, we learned yesterday the physics word for it. Does anybody remember what we call it in physics? The device that converts electricity into something else. It's called a load. You guys recall this? There are three main requirements to make an electrical circuit. One is you need to have a power source. You need to have a battery of some kind, something that gets the electrons moving. Two, you need to have something to conduct the electrons. Typically, that means we're using wires. Doesn't have to be wires, but it's probably wires. So you need a power source, you need wires, and then the third thing is once you have the electricity, that's awesome, but like it has to accomplish something. Okay. Today I'm going to show you how I actually managed to make electricity using just some chemicals. This is the battery out of the clock. And I put the clock up on the table right here because I've got a couple of chemicals working here, and it's actually running our clock instead of the battery. And I think I can use that as the launching point for our lesson because here's a battery. It is capable of producing electricity. And as it is sitting in my hand right now, it is absolutely useless. That makes sense? Because it needs to actually do something. It needs to be plugged in. Okay, so that's my goal today. I want to talk to you guys about two things. First part, how do we make electricity? It doesn't just come out of thin air. We actually have to produce our electrical energy somehow. And then the second half of the lesson is once we make our electricity, what are we going to do with it? Does that make sense? So hopefully in the next half hour, I will have given you guys some thoughts and taught you something new on those two questions. So here's the two questions again. How do we create electricity? What can we do with it? Fair enough? Okay. So I want to tell you about a story about a guy named Michael Faraday. And he is one of the fathers of electrophysics in terms of the discovery he made back in 1831. He was messing around with magnets and a device called a galvanometer. And because of yesterday's lesson, you guys should know what a galvanometer is. So what does a galvanometer do? It measures what? It measures amps. Yeah, it measures current. And so what he did is he set up a galvanometer and he set up a coil of ring in a circle. He wrapped it around in a circle. And what he did is he took a magnet, just a basic bar magnet, and he put the magnet inside the coil of wire. Now, normally you would think, well, there's no battery attached to this. Why would the galvanometer show a reading? But as soon as he moved the magnet inside, it actually caused the galvanometer to move, which meant that there must have been some sort of current. And the current was formed merely by moving a magnet inside of a coil. And this was the first known discovery of what we now call electromagnetic induction. And it actually makes sense the way the words fall together. Electro, because we're going to make electricity from magnets, so electromagnet. And the reason why is that we induced it. The word induction or induce means that like we actually caused it to happen. By us taking this magnet and putting it inside of here, it actually created electrical current. Now, in 1831, I don't think they knew what to do with it yet. But fast forward almost 200 years, and engineers and physicists have discovered that we can now take this basic principle and we can make ourselves electricity. Okay? You guys probably know this, but like the electricity that we have running through our building isn't free. It has to come from somewhere, right? It's not like there's like a magical electricity bank that we just take electricity. We got to pay the power company. The question is, how does the power company make electricity? Well, most of the time, they're making it through this principle of electromagnetic induction. Okay. I've got some more pictures here I want to show you this concept, and then on our lab on Thursday, I'm actually going to show you guys this in person as well. But for now, hopefully the pictures will help. Here's basically the idea. He took a magnet, he put it inside this wrapped up wire, and if he moved it in, current started flowing. If he left the magnet inside, though, nothing happened. And that's why it's called electromagnetic induction, is it's not just about having a magnet inside the wire, you actually have to move the magnet. And therein lies the problem. We can create electricity if we can have a magnet and a coil of wire moving. But who wants to stand there all day and move this magnet in and out of this coil? That's a lot of work. Nowadays, physicists have discovered, well, what if we can cause, say, the tides to do this? Or, since we live in southern Alberta, you guys know all those wind turbines? Really, what a wind turbine is doing is it's actually causing a magnet and a coil of wire to move relative to each other. And the wind moves it for us. And if it can do that, it can create electricity. Okay. So the main concept here is that it led to what we call a generator. And I really should have bolded that word, because that's another word you should know. You guys ever heard that word before, a generator? I mean, I think we call it a generator because it generates electricity, yeah. But again, it doesn't just magically do it. We got to explain, well, how does it do it? And this is kind of the basic premise. It's very similar to what Faraday discovered in 1831, only there's a bit of a modern day twist in how they approach this. Rather than taking a coil and putting a magnet inside of it, they decided, why don't we just have a magnet sitting there, and why don't we move the coil of wire instead? Okay. Faraday's original discovery was keep the wire still, move the magnet. Does that make sense? But does it really matter whether it's the magnet that's moving or the wire that's moving, so long as one of the two items is moving? So the way a generator works is that they actually take a magnet. They actually take two magnets. They have one magnet over here on this side, one magnet over here on this side, and they take a coil of wire that looks something like this. We call it an armature. That's the physics word for it, a coil of wire. And what they do is they spin it around in circles. And so what ends up happening is as the wire is spinning around in circles, sometimes because you're cranking it in a circle, it causes electrons to move through the process of electromagnetic induction. So I've got a couple of pictures here trying to show you this concept. And again, on Thursday, I'll try to actually break out the device to show you as well. But here's the basic idea. If you were to take this coil of wire right here and spin it inside a magnet, it causes electrons to move. Therefore, you're creating electricity. Here's the main concept, though. The faster you turn the wire, the more current you generate. When I think of this in my head, sometimes I think of like how maybe a person or an animal would be running on like one of those wheels, and like as you run on a hamster wheel, it causes the wheel to turn. You guys know what I'm talking about here? Using that turning motion, we can generate electricity. But sometimes it's better for us to use the environment to cause this thing to spin around in circles. And so three of the most common ways that we use now to create electricity are either wind power, hydroelectric power, or tidal power. I'm going to write those out here. This is wind, obviously. The word we give to this is hydroelectric. Hydroelectric. And this is tides. Rather than a person having to spin something in circles, or like a horse. I showed you this picture a while back. Hang on. I know this isn't in these notes here. But do you guys remember this picture way back here? Oh my goodness. How many notes do I have? Lots. You guys remember this picture way back here? We could use this to generate electricity. If these horses were to spin around in circles, all we'd have to do is set up a way for there to be a coil of wire rotating inside. Usually you'd use like a horseshoe magnet. You guys know like a horseshoe magnet looks like this. One side over here is, say, the North Pole. One side is the South Pole. If you could cause a coil of wire to rotate inside of this, you can actually create electricity through electromagnetic induction. But the issue is you need somebody to rotate the wire. Right? So, hence, give me a second here till I get back to this slide. Rather than having humans do it, let's have nature do it for us. This is where we were. So over the next few slides, I want to show you, again, more pictures. You guys can see why I want you to print off your own notes, because most of what I have here is pictures. Right? Pictures describing what's happening. This is a picture of a hydroelectric dam. Okay? Basically, the idea is we take a body of water, we build a big wall, we dam up the water, and then we let a little bit of water through at a time, and as that water comes through, it spins a device called a turbine. Anybody ever heard that word before, turbine? Right? Here's kind of the idea. You've got this big lake of water, and what they're going to allow is a little bit of water to come through this tube, and it's supposed to fall through here. But as the water goes through the tube, as it passes through, it takes like a propeller and it spins the propeller. And that's this word right here. It's called the turbine. Well, if the turbine starts to spin, well, then that's what spins the generator. Now, this picture of the generator is very basic. What are the two things you need to have inside a generator? A magnet and a coil of wire. Spin one of them. I don't care which one you spin. Either spin the magnet or spin the wire. I really don't care, but it'll cause electricity to start flowing. Electrons will start to flow. And so if you hook this up now to the power lines, now we've started to get our electricity. Let me say that one more time. This is super important. So, how do we get our electricity? Well, we need to create motion. Something has to move. Faraday discovered that if you move a magnet and a coil somehow compared to each other, you can create electricity. Like, this is probably the most important discovery in like the last couple hundred years, because if it wasn't for this, we wouldn't have all our technology. Because literally, this is how we get our electricity. Move a magnet, move a wire, we can create current. But how do we get it to move? Well, again, if I show you this picture right here, have a little bit of water go through here and spin a turbine. The turbine spins, causes either the magnet, inside the generator is a magnet and a coil of wire, cause those to spin, it creates electricity. And the pictures of the generator were back here. I should talk about some of the words you need to know. The two words you guys need to know are armature, because that's the word that we give to the wire. So if you want to maybe make a note on your notes if you have them by now. Armature is the word we give to the wire. And it's not on this slide, but I know it's on a future slide. The word for the magnet is called a stator. S-T-A-T-O-R. So those are the two things you need to have. An armature, which is wire that spins. A stator, which is a magnet. Can you guys kind of visualize how then the wind turbines and the tidal turbines do the same sort of thing? As you spin the turbine, it moves the armature, which then creates electricity. Super, super, super cool. Well, this is essentially what happens then in a battery. That's the next thing I want to talk about, is we can also get electricity from batteries. All we need to do is find a way to get electrons to move. And I found this cool little animated thing online, because this is really what a battery does in a sense, is electrons start at one side of the battery, and then the electrons go through the wire, and then they end up on the other side of the battery. And in the process of doing that, if you put a device right here, whatever that device happens to be, again, we call it a load, then that device can take the electricity and do something. And so what I did today, because I'm also the chem teacher, is I actually made a makeshift battery over here. And if you guys would like, later in class today, feel free to come take a look at this. I'll even turn it around backwards, just so you guys know that I'm not lying to you. There is no battery in the clock. This is the battery. I've taken it out. Okay? And I've hooked up two wires to each side of the clock in the back here, so the battery's out. And you guys can clearly see the clock is still running. Isn't that cool? So here's the process. I actually needed 3 batteries for it to work, because 2 wasn't enough to make it happen. Not even 1 was enough. But the basic idea is that of all of these wires, what's happening is electrons are running probably from this one right here through the clock. This is the hot wire, right? Remember how hot wire is the one where the electrons run from? The electrons are running from the hot wire into the clock, and then they're coming back through the neutral wires, and then they're going back into this 3 set of batteries right here. So if you'd like to, come take a closer look later. I should point out, actually, This is one of the questions on your assignment. Dylan, I'm going to steal yours because it's close. Question number 9, no, number 13 says draw and label a diagram of the electrolytic cell demonstrated by your instructor in class. This is that cell, by the way. So I have that written up here at the top here. Another name for a battery is called a cell. Okay? Electrochemical cells are another words for batteries. If you can get electrons to flow, it's a battery. Nick? No, I was going for the one I made in class. So if you'd like, I'll show you guys the battery a little bit closer later if you want to kind of see some of the details of it. But for right now, hopefully you guys can all appreciate that, like, that clock is running and the battery's out of it. It's kind of cool, eh? Because that's really what a battery is it's causing electrons to flow. I've got some pictures on the next few slides kind of showing you the basic premise of a battery. So batteries are often more compacted than this, but at their core, here's what they have to have. They have to have something called an anode and a cathode. Okay? And you guys will know this in a battery because the anode is the negative pole of a battery and the cathode is a positive pole of a battery. You guys know how like there's a plus and a minus on both sides of a battery? Okay? All cells have to have a positive and negative. And the way it works is that the electrons always flow from the negative through the load and then back over here towards the positive. Okay? Now, there is more involved for a battery to work than just that, but I don't need you guys to know this in Science 9. So some of the stuff on the diagrams is a bit more than you need, but you do need to have something known as an electrolyte. Electrolyte. I have that right here, where you have to have a way for the circuit to get completed. You guys remember how we talked about yesterday, in order for there to be a circuit, you need to have 3 things. You need to have a power source, you need to have something to conduct the electricity, and you need to have a load. You guys still paying attention here? Okay. It's not just enough for this picture right here to occur, because this is not a complete circuit the way it currently looks like it's happening, because this needs to go all the way back to where it started from. And right now the electrons are only going from here and stopping here. For it to be a true circuit, it has to go all the way around and then loop back through what's known as a salt bridge to create a completed circuit. So sometimes the electrons are actually traveling through the wire, but sometimes ions are actually traveling through water as well. And that's what I have kind of going on in my battery I've got right here as well. But if you guys could highlight a couple of words or write them down for later, I need you to know these words. Anode is the negative side of a battery. Cathode is the positive side of the battery. And you have to have a positive and negative side in order for this to work. Okay. Here's some of the words that I was mentioning. It's on this slide here if you've got it. Okay. All cells have to have what's known as an electrolyte, which is either a paste or a liquid that conducts electricity. You guys might notice in the cell that I've made in front of the classroom, see that blue liquid in there? That's known as an electrolyte. Ions are still flowing through that electrolyte, not just through the wires, but also through the liquid. If you ever take apart a battery, you'll notice that inside the battery there's like a paste inside of it. There needs to always be a continuous circuit of electrons. They can't just stop halfway. The other 2 things that you have are then known as electrodes. And these are either those anodes and cathodes. And if I can show you guys here on my batteries, each one of these cells here has an anode and a cathode. Okay. Now, I really hope this works because it's going to be embarrassing if it doesn't. If I were to take this out of here, did that stop running? Yeah. Because I broke the circuit. Does that make sense? But if I put it back in, please work again. Stop. Work. Right? We need to have 2 things. You need to have these pieces of metal here. Working? Okay. You need to have your metal electrodes, but more than just the metal electrodes and the wires, you have to have the liquid inside the electrolyte. Okay? So you guys can see, as soon as I took it out of the electrolyte, it stopped working because the circuit broke. So I need you guys to know these words. Electrolyte is the liquid that it goes inside of, and then electrodes are the 2 solid pieces of metal that we have. The positive one is the cathode. The negative one is the anode. Does that make sense? And that's basically what makes a battery. Okay, now I've got a slide on here for a couple of different types of batteries. I would like for you guys to actually look this up because it's one of your questions, I believe, on either an assignment or a lab somewhere. Yeah, it's number 15. There's actually multiple different types of batteries. There's two different categories. It can either be a wet or a dry cell, and it can be a primary or a secondary cell. Okay. I'll give you a hint. This one right here is a wet cell. Okay, but I need you guys to, it's in your textbook. I'd like for you guys at some point to go find the difference between a wet and a dry cell and a primary and a secondary cell. It's actually really easy. It's right in your textbook. But I put this slide on here. I want you guys to look this up at some point. So you guys research these in your textbook. And it is a question. It's number, which one was it? 15 on your assignment. Okay. So there's the two ways that we can create electricity. Option 1.
Alicia Larson, please come to the office for checkout. Alicia Larson, please come to the office for checkout.
Option 1. You can create electricity through a turbine and electromagnetic induction. That's one way you can create electricity. Now, one of the great things about electromagnetic induction is that as long as you have a device that can keep powering the turbine, like wind or water or whatever it happens to be, then that will work continuously. What's the problem with a battery? Eventually, a battery is going to die. Yeah. And I want to talk for a second about what makes a battery die. Okay. Here's one of the reasons why a battery will die. If you guys can see from where you're at here, here's my electrodes. Okay. Wait, one thing you might notice about these ones right here is that this guy right here is starting to turn a little bit black. Hey, can you guys see that? What's happening is one of these electrodes is eventually getting eaten up. It is chemically disintegrating. Does that make sense? And as soon as this thing right here is all chemically disintegrated, the reason why it'll stop is because just like when I lift this guy out of the solution, there's nothing left here left to react. Does that make sense? When a battery dies, one of the chemicals eventually runs out. You get what I'm saying here? And so as soon as either this one runs out or this one runs out, it's no different than me just taking it out of the solution and saying, well, now there's none left, right? Imagine all of this somehow got eaten up. Well, now will it react anymore? Well, no, because you can't complete the circuit. So that's what causes a battery to die. If you guys see a dead battery, you ever notice how sometimes like there's a little bit of like white pastiness on the dead battery? Have you ever seen that before? One of the reasons why is that in a typical battery, one of the way this works is that your anode or your cathode on this battery, one of them is a core that goes right through the middle. See this little like plug that comes out of the top there? That's actually like a rod that goes all the way through the middle of the battery. And then the other one is actually the outside layering. As soon as the outside layering gets eaten up, sometimes some of the liquid will ooze out of the middle of it. And that's because just like this guy right here, you can see how it's turning black here, it's getting eaten up. Eventually it will disintegrate and be all gone. So that's how a battery dies. Let me go back real quick to that picture I've got here. Eventually, let's use this one here. Eventually what's going to happen is this guy right here is going to like wither away. And rather than being here, it's going to disintegrate into pieces. Well, eventually, as soon as all of this disintegrates and you evaporate it, that's not the right word, but as soon as it's all gone, well, then it breaks the chemical cell. Because in order for it to be a battery, it has to be a closed, Jenna, please, it has to be a closed circuit. As soon as you break the circuit, because either this guy or this guy runs out, well, then the circuit's broken and it's done. That makes sense to everybody? Okay, so 2 ways of making electricity. Electromagnetic induction. You can do that infinitely. All you need to do is have wind power and it just keeps pumping your turbine. Or a battery. Okay. Well, the next thing I want to talk about then is, well, what do we do with that electricity? Once we have electricity, how can it accomplish? Well, before I get to that, though, I want to talk about the 2 types of electricity. And maybe you've heard this before. There's AC current and DC current. And that's what inspired the band name, if you've heard of them, AC/DC. Anybody ever heard of AC/DC? Yeah, they're a good band. Thunderstruck. Back in Black. Okay, anyways. If you haven't heard this before, there's 2 different types of current. And it's actually based on the 2 ways of making electricity. DC stands for direct current, where although it goes in a circle, it has to go in a full loop. It only goes in one direction, direct current. Here's a battery. The electrons are going to go through the loop and come back to the other side, and that's direct current. Okay. Now, batteries work on DC current, but most other electricity is actually AC current, which is called alternating current. And I've got this picture here to kind of explain how alternating current works. Can you guys see how as this turbine is spinning around in circles, sometimes the water gets pushed that way, but sometimes the water gets pulled back. See how it's getting pushed, then it's getting pulled, then it's getting pushed, then it's getting pulled. Can you guys see how the water is actually traveling in an alternating direction? Watch it for a little while here. Pulled, pushed, pulled, pushed. If I were to keep track of which way it's going, right now it's going this way. Right now it's going this way. 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 Can you guys see how a turbine, when the turbine is spinning around in circles, how it creates electricity a little bit differently? Rather than it just going one way through the loop, as the turbine pushes around in circles, it alternates. So one of the things I need you guys to be aware of is that a battery, which is also known as a cell, will go this way here. But if you do electromagnetic induction, it makes AC power. I'm actually going to show you guys this in the lab on Thursday, but for right now, maybe I can just visualize it with a slide I have earlier here. This is back to Faraday's basic example of a magnet and a wire. I'll use this one here. When Faraday pushes the magnet into the coil, it causes the current to flow in a positive direction. See how like the needle is going that way in a positive direction? But when he pulled the thing back out again, it actually caused the electrons to flow in a negative direction. And so really what happens is as you push the wire in, electrons flow this way. When you pull it out, electrons flow this way. Push it back in, they go this way, then this way. And so that causes the alternating current as it goes in and out and in and out, or spinning in circles, however that works. So if that doesn't fully make sense to you, I promise you, I'm going to show you this on Thursday in our lab. Okay? But I really hope the water analogy makes sense, that you guys can kind of see how the direction changes. So we've now talked about how to get electricity, either a battery or a generator with a turbine. So the last part of my lesson then is, well, what are some of the things that we do with electricity? Okay. And so I need to remind you one more time, this is really, really important terminology. What are the three things you need in a circuit? You need an energy source. For the sake of today, why don't we just pretend it's a battery? But does it have to be a battery? No, it could be a generator that made us electricity. Okay. You need a wire because it needs to conduct. And you need to have a load. You have to do something with it. My question today is, well, what can we do with it? More than just power lights and stuff. So here's a couple of really cool examples that you need to know about, especially for your PAT coming up. So the first one's called an electromagnet. One of the cool things is that if you have electricity, if a magnet can create electricity, it's actually possible for electricity to create a magnet. And someone really smart figured out how to make an electromagnet, which basically is a magnet that you can turn on and off. Rather than it being always a magnet, if you run a circuit through it, it's a magnet. If you turn the circuit off, then it's not. And so, you guys ever seen like maybe one of these things before where it's like a magnet that can pick up a car for a car crusher? The question would be like, well, how do you get the car off the magnet? They're like super stuck together. Well, if it's an electromagnet, all you do is you flip off a switch and it turns off. And like at its core, this is a really basic electromagnet. What you do is you run a wire in circles through a piece of metal and you turn on the battery. And if you do that, it'll actually make a north and south pole to a magnet, which is super cool. And again, just to do this all on one day, I'm going to show you this on Thursday. Fair enough? Okay, here's another really cool thing that we do with electricity. This is another major one. We can make a motor. Okay, if we have electricity, we can make a motor. Because really what a motor does is it spins something around in a circle. The most common place you might find a motor is in a vehicle. Right? You need a motor in your car to propel yourself forward. And, I mean, new companies like, say, Tesla or the Nissan Leaf, whoever's making electric cars, I mean, the reason why it's being propelled forward is due to generating electricity. If you have electricity, you can then make it run a motor, and that motor can cause something else to move. So here's the basics of a motor. It's actually very, very similar to a generator. They actually have similar components. You're going to have the armature. We've already talked about that. What's an armature again? Yeah, wire, basically. Yeah, it's a wire. Okay. You're also going to have something called a commutator, which I'll show you in a second. And then you have a magnet, which I already mentioned is called a stator. Here's how it works. I'm going to go stand up at the board here. If you were to have a magnet right here and you run electricity through it, what ends up happening is the electricity will actually cause the wire to move. And so what's going to happen in this particular example is that this south pole of the magnet is going to cause this piece of wire to get pushed down. So if you can picture it, this magnet is getting pushed down on the wire. And this part of the wire right here is getting pushed up. So what we used to have is something that was like this. This side here is going to get pulled down. This side here is going to get pulled up, and it's going to cause it to start spinning. Here's the problem, though. According to the way that this would work, all that's going to happen is it's going to spin 1/4 turn. It's going to sit like this. Can you picture that? This is going to pull it down. This is going to pull it up. And so as that happens, it's going to cause this wire to spin 1/4 turn and sit like that. Well, that's not very useful. I want it to keep spinning in circles over and over again. That's where this commutator comes in. Okay? And I don't need you guys to fully get this, because this is kind of challenging stuff. You need to know just the basics here. Can you guys see how there's like a little split right down the middle here? Okay, here's what this does here. Right here is your battery. This is your circuit right here. And what happens is, if you can picture this, after this is rotated 90 degrees, I'm not the world's greatest artist, but maybe I can draw this. This part will now be up. So it's almost like you're going to have your ring like this. It's going to be up in the air. You guys kind of picture how this has been rotated 90 degrees up? But what's going to happen is this little split in the ring is now going to line up with your wire. And what's going to happen is, for a brief moment in time, the electricity is going to turn off. Not because you turned off the battery, but for a brief moment in time, the wires will not line up anymore. Can you kind of see that? There's a gap right here. And so when it's completely vertical, there's a gap. And what ends up happening is the electricity turns off for just a second. Well, then natural momentum will cause the thing to keep rotating. And so I'm going to go back and put my hand up on the board again here. It was supposed to be flat, and this side here forces it up, and this side here forces it down. Well, if it keeps rotating a little bit past where it's supposed to go, well, then this side's going to keep forcing my hand up, and this side's going to keep forcing it down, and it'll actually cause it to keep spinning. It's a really clever design. Okay. I've got a couple of electric motors in the side cupboards here. Maybe after I finish the lesson here, I'll kind of show you guys how this is supposed to work on an actual physical model. But that's kind of the basic idea, is that if you take electricity, run a wire through magnets, you can actually cause something to spin. Well, then that spinning then runs the tires on your vehicle, right? And that's why you propel forward. Okay. I have an analogy to help explain why this commutator has to happen here on the next slide here. I just want to fast forward to this slide here. The idea behind a commutator is challenging for a lot of kids. So here's the analogy I found. Imagine that you're trying to steer a car. Okay, you got both hands on the wheel at 10 and 2, because you're a good driver. You're doing what you're supposed to, right? Not one hand at 6, but 10 and 2. Okay, let's say that you want to start spinning the wheel. Okay, so pretend I got a wheel in my hands. I'm going to start spinning the wheel. If I want to make a left-hand turn, I can go to about here, and I can't do the rest, right? Because eventually I get stuck. Well, that's what the commutator does, is eventually at some point here, you're going to have to let go and then keep turning. Can you guys kind of get that idea there? That's what the commutator does, is as soon as it gets to the stuck point, it turns off the electricity for just a second so that it can re-grab and start again. Okay. Well, hand over hand or just both at the time, it's the same sort of idea here. So that's why there's this split in the middle there. As soon as you get to the stuck point, where when you want to try to turn it right here, it turns off the electricity for a second, and then you start again. And then you start again. And it just keeps spinning in circles. Okay, I think there's only 3 more things left on my list, and I'm done my lesson. Another thing you guys need to know about is called a transformer. Okay, when we get electricity from the source, especially from a generator, it usually is being transmitted at like say 5,000 volts, which is a lot of voltage. Now, keep in mind, what does voltage really mean? Voltage is about how much energy you have. Okay, it's not actually voltage that kills you. It's amps that kills you. Amps is how much speed it's traveling with in terms of like what gauge of wire you're using. How big is the hole in the water tower? Okay. But voltage is about how much energy it needs to have. Now think about this. If the electricity has to come all the way from like a dam all the way to your house, we better give it a really good push. Because that's really what voltage is. You guys recall that one picture where there was, here, I'll go back and find it. Where is it? Here it is. This picture here. Voltage is the energy that gets the electrons going. Voltage is what gives it a push. Well, if the electrons have to travel in wires for like 10 kilometers before they get to your house, you better give them a good push. Does that make sense? Because otherwise the resistance will eventually slow it down, and by the time the electricity gets to your house, there won't be any power left. Does that make sense? So overhead power lines need to get a really good start by having a high amount of voltage as their push. But the problem is then once you get to your house, we don't usually want to have that much voltage. 50,000 volts is way too much. So we need to use what's called a transformer to either bring the electricity to a higher voltage or to a lower voltage, depending on what you want. And so here's a picture of basically what a transformer looks like. The way a transformer works is it's one of 2 kinds. It's either a step-down transformer or a step-up transformer. Okay. Stay with me, guys. I'm almost done, I promise. We're getting close. This picture right here would be an example of a step-down transformer. And the reason why is look how many curls there are on this ring right here. And then over here, see how many curls there are. See how there used to be like 1, 2, 3, 4, 5, 6, 7, 8, 9 curls right here and down to 3? This is how a transformer works. It takes some electricity right here and it reduces it. Whereas this one right here, if it goes from 3 coils up to 9 coils, it steps it up. So this one is a step down transformer and it reduces the voltage. This is a step up transformer. It makes the voltage higher. Does that make sense? Okay. The last thing I want you guys to know about. One of the other cool things we can do with electricity is we can use it to electroplate stuff. I put some pictures on here of some things that have been electroplated. For example, this is gold-plated silverware. Now, the entire silverware, guys, focus, I'm almost done. The entire silverware is not gold. All they've done is they've put a thin layer of gold on the outside to make it look nice and shiny, but really it's gold-plated. This is chromium. We put a lot of chrome on like things like vehicles because it looks really shiny and looks nice, but the entire thing is not made of chromium, just the outside. And I want to show you how to electroplate something. It works like this. Okay, here's how it works. What you do is you use a battery, and the battery causes electrons to flow, just like we've learned about. And so what's going to happen is electrons are going to flow from this core right here through the battery over to here. And there's going to be a whole bunch of electrons on the surface of this metal. And what happens is those electrons then snag and attract all of these particles. And these particles then coat the surface of the metal with something new. So whatever particles are in this solution, like say this is gold right here, these gold particles attract to the metal right here, but only the outer surface then gets coated with gold. The inside core right here is still lead or nickel or something like that. I got more pictures to show you. Here's one last one here. What you've got here is this is your object that's made out of, say, lead. And then in the solution, you have, say, gold ions. What happens is as electrons go through the circuit, electrons show up over here on this metal right here. And when the electrons show up over here, these ions right here attach themselves to the electrons, and they coat just the outside. So the inside is still lead or nickel or copper, but the outside is something valuable like gold or silver or chromium. But it only works because electrons travel through the wire. I think that was my last slide, right? Okay, I'm done. I want to give you guys half an hour today to start working on stuff. Let me do a quick summary of what we've learned today. The very, very first slide, I think I had 2 questions. The questions were, 1, how do we get electricity? And then 2, what are some of the things that we do with electricity? Okay. 2 ways of making electricity. Option 1, electromagnetic induction using a generator and a turbine. Hopefully that's something that makes sense to you, but if not, I will try to show you more hands-on in our lab on Thursday. Okay. 2, a battery. A battery, though, uses direct current. And one of the downsides is eventually a battery will die because one of the chemicals will eventually rust away and get eaten up and run out. Okay? This clock will not run for forever. Eventually this battery will die. Okay? Those are the 2 ways. The second thing I need you guys to know about, though, is then what can we do with the electricity? Now, the things I talked about today is not the entire list, but hopefully now you have a little bit of familiarity with like how a motor works, how to electroplate something, how transformers work, you know what AC and DC current is. Does that make sense? So that's all I got for now. Guys, this is more than half of our unit. So going forward, I want to give you today and tomorrow to do some practice to make sure you get it. Thursday, I want to try to show you tangibly in a lab how this works. And then next week, Monday, we're going to try our first quiz. Does that make sense? Let me give you guys some parting advice then. In our chemistry section, I think it'd be fair to say that some of you guys didn't prepare the way you should. So I strongly, strongly, strongly recommend finish this assignment. Make sure that it makes sense. Ask me questions. Rewatch my YouTube videos. Do these sort of tasks so that you're ready. And then when we write our quiz on Monday, this is the most important part, and some of you guys aren't listening. When we write our quiz on Monday, you cannot just leave it. You have to go over it with me, or at least by yourselves. But you have to go over your quiz and figure out what did you not get so you can make improvements. Does that make sense? So I don't have any more curriculum to teach you guys, so I'm going to give you guys the next half hour here. Do whatever you want to do. If you want to go work outside, that's fine by me. Some of you guys are already well distracted. Okay. Guys, I'm going to let you make your own choices, okay? But try to make good ones. I'm trying to give you guys the tools you need to do well. Okay, so go ahead. Do what you need to now.